Let you wait for another 1 or 2 minutes, then we can start the event.
Sure.
Good morning, everyone.
Yeah, good morning, sir.
Good morning. Okay, I, Dr. Manoj Kumar Singho, I'm an assistant professor at SRM University, AP. I, on behalf of entire ECE department at SRM University, AP, welcomes you for the ECE department Distinguished Industry Academy Interaction Lecture. This is the first lecture series that we are conducting today. Today, we have a presence of Dr. Shirin Banerjee. She is the master researcher at Ericsson Research. She will deliver the talk today and interact with the students and all the faculties. The students not from the SRM University, it may be from any other universities also, as well as the faculties or other members. They have questions, they can write down the questions in the chat box as well as in the question answer box. In her brief introduction, Dr. Shirin Banerjee is presently working as a master researcher at Ericsson. She has 17 plus years of industrial experience. She joined the industry after completing her PhD from University of Texas at Austin in 2004. Prior to that, she has completed BTech honors in electronics and electrical engineering, electrical communication engineering from IIT Kharagpur in 1999. At Ericsson, she is focusing on developing AI/ML algorithms for radio access network. Prior to Ericsson, she has worked with several industries like Texas Instruments, HP, and Johnson Controls. She has 23 peer-reviewed publications and 9 granted patents, and several patents are pending. Initially, she was working on image processing. Now, presently, she is working on the signal processing area. She will deliver the talk on AI/ML, best interference diagnostic and mitigation for improved quality of service in radio access network. Before starting the lectures and interactions, I also welcome our panel members, Dr. Indranil Hathai, Assistant Professor at SRM University, AP. He will coordinate the question answer sessions and interactions among the students and all the other faculties and other presents. And also with Dr. Shirin Banerjee. We have also other panelists, Dr. Anush Deshpande, Dr. Durga Prakash, Dr. Sunil, and our HOD, Dr. Ramesh Vadi. If anyone has any questions, kindly write them in the chat box or question box. After the question answer, after delivering a talk, we'll discuss the questions. And also, if you have any questions, if you have any doubts relating how, because she is working in the industries, and students, mostly the students, if you have any doubts and you want to interact, how to join the industries, you can ask directly to her. Okay, I kindly request Dr. Shirin Banerjee, please start the talk.
Thank you very much, Professor, for the kind introduction. Let me share my screen. Can all of you see the slides and hear me okay?
Yes, ma'am.
Okay, okay,
Fine.
okay. So, yeah, like Professor said, if you have any questions, you can type it out in the chat box. But if you feel like something is unclear and you want to ask while I'm speaking, please feel free to interrupt me and ask the question. So today I will, be giving you a glimpse of what all the things we are working on. I joined Ericsson 3 years back. So there are many things which I am also learning in this exciting journey, but I'm very thankful to SRM University for this invite. And I'm very happy to share with all of you. So this work, though I am part of the research, before joining research, I was a part of Gaia, a global AI accelerator in Ericsson. And most of the work which I will talk about today were done with my colleagues in Gaia. So Art Brissabois, then Joy Bose, Ranjini, Sliba, and Pratyush, they were also involved in this work. So what happens, I'm not sure how to get rid of the stop bar, but hopefully it is okay. So what happens is we all have our phones and our laptops, and these phones and laptops get connected to the base station. So base station is basically all the antennas that you see while going on the road, right? There'll be like tall towers or round towers. So those are the base stations and the antennas. So what happens is as soon as a phone comes in the vicinity of an antenna, the antenna sends a signal to the phone. And based on that signal, the phone or the laptop, it does some measurements. Say, for example, antenna sends a signal worth of 10 dBm. So the phone will say, I just received only 5 dBm. And then it will send the report back to the antenna. So that way, an initial communication is established, and the base station understand that, okay, this channel is very good or say very poor. For example, when you go to a mall or a lift, you will often see the phone or the quality of the call is dropping, right? So that is how the estimation takes place. So everywhere we go, everywhere we move, there's a constant signaling between the base station and the user equipment. And then the base station gets an estimate, how good is the channel, and based on that, the remaining communication happens. Now, one thing which is very expensive is the frequency which is used in the communication. So that spectrum, we call it in technical terms, it is very, very expensive. So what happens is many base stations and many user equipments will communicate using the same frequency. So what happens in that though your phone is communicating with one particular antenna, all surrounding phones which are in the close vicinity, they are all receiving the same signal that you are receiving, because ultimately the communication is happening through an air channel, right? So a signal which is like a serving beam for one user equipment also becomes an interference pattern for all other surrounding user equipments. So that's why there are many technologies, and that's the primary focus, that if you have too much interference, basically many times this also happens, right? When we are talking, we hear somebody else's voices. So that is, the interference has become so strong that we cannot even differentiate like what is the signal and what is the interference. And it thinks that the interference itself is the signal. But most of the times it doesn't happen. So that's when, we are taking care of the interference. So what does the antenna do when such a thing happens? So it can basically tilt the antenna and it can change the power level. So it's like this. Suppose you have gone into a crowded room in the party and you're trying to talk to someone, and that person tells like that person cannot hear you. So what's the first thing you do? You try to talk in much more loudly, right? So this is the same thing which antenna does. So when they say that, okay, the phone is sending back that I cannot hear the serving beam, all it'll do is it'll increase the power. So when it increases the power, what happens is this coverage area means the area under which that antenna is covered, increases. So the good part of increasing the coverage area means more phones which are there in that area will be served by that antenna. But the downside of increasing the coverage area is like from a nearby base station, you will have this overlapping region. And this overlapping region is very problematic because, the interference will be much higher in the overlapping region. At the same time, you cannot, decrease the coverage area so much that there is no overlapping region. If there is no overlapping region, and if a phone or a laptop comes in that region, immediately you will get a call drop. So these are, various things we can adjust, and there is no universal, adjustment that, okay, from this time of the day, I've adjusted my parameters to this much, and after that, everything will be fine. It's a very dynamic environment. Like even during the day, the traffic pattern changes, the temperature changes, the noises change. Say, for example, high-speed train is going, we are on a high-speed train. So it's a very stochastically, very, very diverse environment. So continuously whole day, though we don't know, when we speak to a phone, we don't think about these things, but that is what is going on in the background. Again, there are cases like we may be watching a video. At that time, if a delay happens, we won't mind. But when we are talking to someone on the phone, we want to hear every word. We want to make sure we don't miss any word, right? So depending on the context also, these things change. So behind our background, the whole connected world of base stations, and that is where what we do in Ericsson, we kind of take care of the entire background network so that every call, every video input, all the communications happen seamlessly. So today I will talk about what AI ML can do to improve this. So traditionally what is done, basically there are lookup tables, there are rule-based parameters, and most importantly, there are radio engineers. So they can predict patterns. So they see that, okay, for 7 days, this area had a bad coverage. For example, there was a landslide and all the base stations were shut off. So they will manually reroute all the calls. So what we are trying to do here is just automate that process which a human operator does, and can we use artificial intelligence to do the same thing? Okay, so that's the motivation. And there are two kinds of problems. One are like the static parameter changes, like I mentioned, the antenna tilt, the power, because once we make a change, the effect of that change will be static for some time, right? For example, if I change the tilt of the antenna and the coverage area increases, it will remain there for some time. It will not suddenly change. But there are more changes which are more dynamic in characteristics. So one of them is passive intermodulation. I will talk about it. And one of them is traffic. Like in a mall, it will be a high traffic zone. On a high speed train, it will be a very fast changing high speed UE, which will be, which the antenna will see, and all those things are there. So, yeah. So when we change a static parameter, the effect of that change will be persistent in time for some time. So if the cell is already undergoing a lot of traffic, at that time we will see an interference pattern like shown in green. Like every time the traffic increases, the interference increases, again it decreases, and you see this, this rough mesh kind of thing. Like at all energy levels, you can hear the noise. So that's not a best time to change parameter settings. So people traditionally, what they do, they take a night time when the activity in the surroundings is pretty low, and then they find out intervals when the cell is undergoing relatively static interference. So as shown in the red line, it's like, you see, it's not very fast changing in time, and neither it is spread over all energy levels. So when this kind of pattern happens, typically in the night or when there is not much traffic, they make the changes and then they simulate. They simulate that, okay, I have made the change, and I simulate some traffic and see that whether the change is good or not. So what we want to do with AI/ML, we don't have to wait for night. We can analyze both the traffic and the interference pattern as and when they happen, and then make the change. So the good advantage of doing this in an online fashion is like, we don't have to wait for a problem to happen and then, wait for the night to come and do the processing. We can do the processing like as and when the problem occurs. Was there a question? Okay. So what we did is like, first of all, we can boil down the problem to, this is a interference pattern classification problem. So there are two types of interference. One which can come from the traffic or the passive intermodulation, which is kind of rapidly changing, spread over all energy levels, or the other kind of interference, which is kind of static in time and not changing too much in the energy levels. So we did a random forest classifiers and we used an L1 norm. The reason L1 norm worked better because it's, as you saw in the previous slide, it's pretty much a straight line, right? So instead of L2 norm, L1 norm was better at finding out that straight line. So here are some results. So we usually labeled the training samples as whether it was static or a dynamic interference. And with the random forest classifier on an unseen test set, we had over 94% accuracy. So this was the first job solved, that we can find out interference when the cell is relatively undergoing a very static interference. So post that interference, what we can do? So then what we did was we divided each of these antennas into clusters, and a neighbor is defined by a neighbor which gets maximum number of handovers from a particular cell. So if cell A gets maximum handovers to cell B, then cell B will be its first neighbor. We can also do this based on geography, but what we have seen, there are many physical phenomena. For example, like two base antennas can be close by, but maybe there is a water body in between. Then though those antennas are close by, since reflections and refractions happen in the water, that antenna will appear to be much farther away. So maybe another base station which is geographically far apart, but there will be much more handovers on that, base station. So that's why handover is a better mechanism of finding out which is the correct neighbor. And once we form these neighborhood clusters, we find out clusters which have a good signal to noise ratio. So the plot in blue, which I'm showing here, so that is the signal to noise ratio. And these values change from 4 to -4. So 4 is a good value. Anything above 2 is a very good value. So you can see in the teacher clusters, most of the cells have very good SINR. Now, another set of clusters will be there where at least one cell in the cluster will have a low SINR. See, all these values are 2 or below. So now what we do is like, okay, we have already find out places where the interference is static. We have another regression model, which from these teacher clusters it finds out the relationship between the power and the SINR. And even from, domain knowledge, this relationship is a linear relationship. But instead of just fitting it with equations, we used a regression model which learns this linear relationship. So once we have trained our model on the teacher clusters, we can use the trained values and then apply it on the student cells. So if in the student cells, the SINR is low, it will adjust this power setting as shown in red and then change it so that the SINR also gets fixed. Okay, so that's what we did. We had learned the regression model from the teacher cells and then we applied it on the student cells. So as you can see from the results here, like there were 2 baseline approaches. And the problem with the baseline approaches, the values they were recommending was very high. And very high has a trouble that you may burn a lot of power. You may, that you may burn the antenna very quickly. And another thing is like if you increase the range too much, like there will be a lot of interference in the neighborhood. So as you can see from our results in yellow, we didn't have a significant change, but with a very small change, we were able to correct the SINR values. So we validated our method on 50,000 plus cells from a customer network. And over 1 year worth of data, we saw that our algorithm did better than state of the art. So we did a SHAP analysis explainability also to explain, okay, whether the features we were using, both from a domain understanding point of view and whether it complies to the domain. And we saw that that was indeed the case. All the values it recommended depended on the interference and the neighbor's interference. And that is what we learn even from the domain. So that way, our algorithm was very compliant to what is known in the domain as well, and it gave better results. So why did we do better? The question can be. So the reason is what other people were trying to do. They were trying to take the data that comes in from these base stations, and then they were trying to fit one kind of AI ML model, maybe it's a graphical neural network model or some kind of model. The part where we did differently is we tried to find out that what a human operator would do. Instead of blindly applying one algorithm to the data, we went and talked to engineers and found out like how a person would actually fix the issue. And what we did differently is we automated just as if the person would do. So that is what differentiated our work, and we were able to show that we get significantly better results. So now that hopefully it is clear, if there are any questions up to now, I can take it. Okay, so that was the part about static interference. The other part, like I mentioned, is the dynamic interference. So dynamic interference can occur from two types. One is traffic, like, okay, we have say 9 a.m., all the people want to go to office at that time, we will have huge traffic. So our interference and all the network parameters will change. Another very interesting feature is passive intermodulation. So let's first discuss how it happens. So what happens is like we have something called carrier aggregation, and especially with 5G, we will have more of that. So what people have found out that if you use only one particular frequency to communicate, there's so much throughput you can get. But if the channel is very good, you can communicate, you can like combine multiple frequencies and send those communications on parallel frequency channels. So even if like one frequency channel is not good, the other channel will take over. So that was the main reason behind carrier aggregation. Now it comes with a problem. So we all learned about resonance in school, right? So if we play loud music, we see that all the shells also start vibrating. Or if any of you dance, when you dance, you see like all the glass and everything starts vibrating on the side, right? So same thing happens here. The moment we say that we'll combine multiple frequencies and start communicating, all these frequencies and harmonics of them get added up, and they start shaking the antenna. And also we will see like there are metal rods on which the antennas are mounted. Plus there are metal nuts and bolts and screws. So all of those start vibrating at a very high frequency. So now the base station has a very high power, and it can communicate to the phone. But our phones, they are like much lower power devices, and we don't have like, or we always don't operate the phone or the laptop in full battery mode, right? So the signal which is coming from the phone to the base station is very weak to begin with. On top of that, you have a very highly vibrating noise which is very close to the antenna. So all this noise and the combination harmonics of them, they go and fall into the uplink. So what happens is the antenna is not hearing your phone anymore. It is hearing its own noise and thinking that, okay, that is my correct noise. So all the estimations go for a toss and your call drops. So that is passive intermodulation. So, and the problem with this that, now say you have, so what do people traditionally do? So traditionally what people do, like Airtel will have dedicated radio engineers who will try to detect when a passive intermodulation is happening. And then the, engineer will go and manually fix some screws and take care of it. But now with 5G, like we have carrier aggregation, right? Even if you have fixed it for one frequency, during transmission, like another frequency can create a problem. And there was another thing which was invented way in the Second World War. So that's called frequency hopping. And the good news is it was invented in Second World War, but it's still used today. So that method says that I won't keep my frequency, which I'm using, steady for a long period of time. After every 40 milliseconds, I will go and change my frequency. The reason for that is, suppose somebody is trying to break the channel and find out what I'm sending, they will have a very hard time because I'm, constantly shifting. So it's very hard to catch a, fast changing frequency. But that makes passive intermodulation very difficult, because even if you have fixed for a particular amount, that frequency will again change in 40 milliseconds. So how do we deal with it? So like I mentioned, like this is the one signal shown in red, that is the interference of the primary cell. And the one signal shown in green is the interference of the first neighbor. So this is a 7-day plot. So you see, like during the night, the interference is decreasing, in the daytime it is increasing, and so on. So 6 out of 7 days, the primary cell and the neighbor did the same thing. But on this particular day, actually there was an event. This is a data from Japan, and there was an event in Japan. So if both the green and the red line, both of them increase, then we can see that, okay, that the event caused it. But you see a funny characteristics here, that there was no change in the green characteristics, but only the red interference increased a lot. So this is primarily due to passive intermodulation, that we won't see an effect which will be visible across all the nearby base stations. Only one of these base stations will suffer from this problem. And what happens, the plot in blue, like, the SINR kind of decreases whenever the interference increases by a large amount. Another typical characteristics of PIM, like the noise from the traffic, you see it's pretty much within a range. But PIM noise increases 3 times. So if you increase the power by 1 dB, you will see the PIM noise to be increasing by 3 dB. And that's what we see in the plot, right? There was suddenly a step up jump in noise. So what we said that, okay, why don't we apply a time series model, and we can find out PIM exactly when it happens. So we don't have to do a priori fix in the late night, or maybe a radio engineer. Sometimes we heard, people, when they manually try to detect these PIM regions, it can take from 4 to 5 hours to just even locate which antenna is giving this noise. But here we said, okay, we deploy this algorithm on all the cells, and the algorithm can figure out and tell you, okay, this antenna is giving PIM, so the engineer can go and address it. So the cell below here is like, maybe like the manual engineer was able to figure it out, that this one of the cell was causing a PIM. And as soon as the PIM noise was fixed, you see the noise significantly reduced and the SINR increased. So here is how we address the problem. Like I mentioned, like there are hardware tools, there are dedicated engineers, all of these cost a lot of money. And even more than money, it's like they have to do that in the maintenance window in the night. And the characteristics of the maintenance window and the daytime may not match. So what we are proposing is an online approach, is a as and when it happens approach. So that way it's like, much better. Like you can solve the problem as it happens. You can solve it like even within the span of 40 milliseconds. So what we did here, we said, okay, let's analyze the time series through all possible ways. So first we had like distance-based method, and here we use dynamic time warping. Then we had frequency-based methods. We showed 2 approaches. One is based on wavelets, and one is based on short-time Fourier transform. And then we had sequence modeling-based approach, which was with the hidden Markov model approaches and LSTM approaches. Because depending on the noise, I'll show you in the next slide, one or more of these approaches will give about 60% accuracy. But then we combine these approaches with a confidence-based measure, and this measure can feed back and tell how the environment is. If it's too noisy, then frequency-based methods will not work. I'll show in the next slides. So this combination of all the 3 types of methods gave close to 100% accuracy. So this was our, whole block diagram. We first had the interference classification. If it was static, we adjusted the power corrections. If it was dynamic, we sent it through these 3 approaches. And once we have results from these approaches, we combine them. And then there's an incremental learning where we can, adapt the thresholds as and when the signal changes. So here are a few examples. Here, the primary cell interference is shown in red. We see that there are, these isolated peaks, which happened only on one cell, not on the neighbors. And this is a pretty clean signal. So here, both dynamic time warping, the wavelet based, and the hidden Markov based method, all the 3 methods were able to give good results. So this was an easy case. This was a case when the cell had noise like shown in the red peak, but the other cells also were quite noisy. And the noise was also fast changing. So in the frequency domain, here I'm showing wavelets. That cell kind of showed that, okay, it had the frequency patterns all over. So it was very difficult to, isolate this frequency pattern, like this noise pattern. But dynamic time warping gave a better results. So here also, that's the power of the ensemble, that though one of the method is not working, the other methods will take care of it. This is an example where we have and this is very common, we have missing data. So many times what happened, with age or something, like maybe the power was too high or some, sensor got burnt, we stop getting data from a particular base station, and there'll be periods of time when you will have missing data. So when we have these missing data, then distance-based methods, dynamic time warping based methods fail. Like it showed a peak in the missing data area. But here the frequency-based method and the hidden Markov model-based method did well. So these are the scenarios under various conditions, and these scenarios can change with time. So in summary, that's what we were able to show, that though the individual methods are not very accurate, when we take the combination of them and the system learns incrementally in an online fashion, we are able to get close to 100% accuracy. So now the results that I showed you, these are called key performance indicators. So they are captured at every 15 minutes, one sample is captured. But all the signaling and back and forth signaling, which I talked about, it happens at 1 millisecond level. So if we just think that, okay, we will take an algorithm which is working in 15 minutes sample data and we want to further down sample it, there's a problem with neural networks. So that problem is called spectral bias. What it says basically, when a neural network sees a very fast changing signal like this, it typically thinks that that is coming from noise. So what it does is it has a kind of averaging effect, and it will try to remove those fast changing pattern and try to approximate that signal with a much low frequency signal. So there are two ways we can solve it. One way is from the data point only, instead of giving a very fast changing signal, we can aggregate the data. Like for example, 15-minute sample, we can combine 4 of them, make it to 1 hour, and combine it further, make it 12 hour and so on. The downsampling of aggregating the data, like you see on the left, whenever you aggregate the data, there'll be an averaging effect. So these are the peaks we want to detect, but whenever we kind of take the signal and average it out, we get very blunt peaks, and then the whole purpose fails. Like if you get a blunt peak, you cannot detect where was the problem. So we took 7 state-of-the-art algorithms, and here I'm showing you 3 results. You see, if we don't do anything, all the results that we get from forecasting are pretty blurry. So the red line is an approximation with a very low frequency line, not even close to the real signal. Same here. And the only thing which performed was a Sari-Marx model. But again, Sari-Marx is a statistical model, and it assumes a linear relationship. So if we have non-linear characteristics in the signal like this, it's very hard for Sari-Marx to quantify that. So here what we did, we took inspiration from a work in Google. So basically, their problem was they wanted to show a image from low resolution to high resolution, and you have the similar problem. Say you have very sharp whiskers on a cat, and when you blow it up just like that without doing anything, those details get blurred out. So they were using a frequency bank approach. So basically you take the signal and break it into 256 frequency banks, and then you pass these frequency banks to the multi-layer perceptron. We did a similar thing. So we broke the time series into frequency banks and then used the multi-layer perceptron. So as you can see, the red one is the original signal and the blue one is the forecast, and it's pretty much doing well, much better than any of the algorithms which I showed you before, right? So here we were able to make a significant advantage over state of the art. So similarly, again, this scales. Even if we have 1 hourly data, there also the forecasting is pretty good. now that we have the technology, what else we can use it for? So we can also do an auto encoding. So auto encoding, basically, like we can take all these time series signals and have smaller representations. And the good part of having these representations is you don't have to send the whole time series representation. You just send the auto encoded part, and the decoder will be able to reconstruct that. So if we didn't do any Fourier feature mapping, we see from the state of the art, I mean, auto-encoded all gives 0 output. This is again coming from the spectral bias. The neural network thought that these were all noise and approximated it to 0. But when we use this approach, we see that our results are much better than state of the art. So this work can also be move to Granger causality. Granger causality, okay, if multiple problems happen in the network, there's usually a pattern that maybe like the traffic increased first, and that led to power outage on one particular antenna, and that power outage led to throughput degradation in another antenna. So all these anomalous effects, they are not like independent of one another. There's a very, most often there's a dependency. So what we are using this is like we are trying to find out the causal relationship between those anomalies. So again, there, Granger causality is traditionally a linear relationship, but using Fourier feature mapping and neural networks, we are able to find out non-linear relationships between the anomalies, and then provide a root cause analysis to the operator. Okay, so yeah, so far I have talked about something which is called reactive maintenance, that okay, anomalies or forecasting things happen, and then we detect, okay, at this point this problem happened. And even better proposition would be to have a predictive maintenance. Predictive maintenance is like, okay, even before a problem happens, can we anticipate? Like, okay, suppose there's a cricket match in say in your university, there's a big cricket match. So on that day, pretty much you will have a lot of crowd, right? So it's very likely that a network will go down. So can I even forecast like this anomalies even before they happen, and then kind of pre-correct all my parameters to take care of that problem? Like I showed you in a previous slide before, like on Japan, on that day there's a big boat event in Japan. So you will see like, okay, most cells had a trouble in on that day, on that boat day in Japan. So if we can forecast that, okay, this problem happened 1 year back and boat days coming up this time also, can we do a predictive maintenance and do the corrections accordingly? So for this, we use the self-supervised learning approach. What we did is like, okay, using our ensemble approaches, using our Fourier feature mapping approaches from time series, we can mark anomalies. And now we map all the time series, underlying time series. It could be load, it could be temperature, it could be time of the day. All these time series have a map from that to the anomalies. So that becomes a regression model. Okay, so this kind of pattern of traffic during the day, or this kind of temperature during the day had given rise to this anomaly in the past. So that becomes a regression model, and we keep that regression model as a critic network. And then we have a actor network, which tends to revise the model. So based on historical data, there'll be a combination of actor critic methods, which will map all the underlying time series to these anomalies. So the good thing of this mapping is that next time, if we forecast that, okay, if we are forecasting that such and such day will have a high traffic, it's very likely that again we will have high traffic, means again we'll have a throughput degradation, because we have seen that data in the past. So then, so we forecast the anomalies even before they happen, and then we have a band depth based validation method. So whatever we are forecasting, we can see whether the forecast was correct or wrong. So here we saw that this whole system was able to forecast anomaly 60% of the time, even before the event happened. And again, same loop, like once we have the validated samples, we can take the samples and feed them back in. So this was more of like, predictive maintenance part. Like, okay, even before the anomalies happened, I don't have to wait for an anomaly. The human like beings always do that. I mean, when we talk to network engineers here, they can say that, okay, if the pattern is trending this way, it's likely that something bad will happen. So this is something which we wanted to do with the self-supervised reinforcement learning approach, that, okay, can the AI agent also predict anomalies even before they happen and take corrective actions? Okay, so this was more for predictive maintenance. The last work which I will discuss about is, okay, so so far we have talked about that, okay, when static interference happens, how can we change the power? Then for dynamic, we have discussed, okay, we have discussed one ensemble approach. We have discussed one Fourier feature mapping based approach where we break the signal into frequency domain and then do it. We have also discussed predictive maintenance, that even before the problem happens, we can fix it. Now, like I was mentioning in the beginning, like suppose Airtel buys our solution and Vodafone buys our solution. Individually, they can, take care of all these problems. But for business reasons, for safety reasons, for 1,000 reasons, Vodafone will never go and tell Airtel that I'm using this frequency at this particular time. I mean, it cannot happen. Like, not all the operators in the world will share their frequency and share their secrets with one another. But it's very likely in a practical setting, like we will have a Vodafone antenna and we will have a Airtel antenna side by side. So no matter what, corrections these operators do offline, when they come and try to do that online, they will like create problems for one another. So it's more like students can take an open book exam, but if there are easy questions and all the students answer the easy questions, teacher will give very less marks, right? If some student is attempting a harder question, teacher will obviously figure out, okay, that person probably knows more. So same here, like, okay, all these operators are internally competing with one another, so they won't share their knowledge, but at the same time they don't want Airtel call drop to happen just because Vodafone use some frequency somewhere. So the problem boils down to, I don't know what is the problem, but I have to still fix it. So what do we do about it? So here we had a very smart binary search based approach, because again, like I mentioned, it will change at every 40 milliseconds. So I can't have a very slow thing, learning and then trying to fix it, because by the time I detect, okay, what's the problem, the frequency has changed. So what we proposed is a very fast binary search based method. So what it does is, like, when it allocates the frequency, it blanks the top half and then finds out whether the problem is mitigated or not. Then it blanks the bottom half. And similarly, once, it has done the top and bottom, it further subdivides into two. So here we were able to show that we could finish the whole process in 12 milliseconds, which is way less than 40 milliseconds. So using our, proposed this binary search based method, which is very fast, very accurate, even without knowing frequency of a neighbor, you were able to mitigate the problem. So that's all I had. I think this is my last slide. Yes. So there are a few questions. I'll take them. But going forward, what we are doing is, right now, my work is more focusing on causality. We are doing causal discovery of problems, causal inferencing of problems. And there are, very, like in research, we are having a lot of interesting problems. We are also doing validation of the methods. Okay, when a human was there, traditionally, when a human was there, a human changed something. And, if something bad happened on that day, first of all, telecommunications is very dear to heart, I would say, of people. If something bad happens, it comes out as a news flash. So if something bad happened and came out of a news flash, you can always go and catch hold of the person who changed the setting, right? If an AI algorithm changed the setting and something bad happened, you have nobody to come and catch you. So that's where, research is focusing on. Primarily, can we validate the method? Like, instead of directly applying a model, Can it tell that, okay, there is a possibility that the model also may degrade performance? And if that happens, who will be responsible for that? Can we have safe experiments? Like, okay, we can guarantee that, okay, nothing bad is going to happen. Either it's going to improve or it's not going to do anything. So those are, three features which we are exploring deeply in research. One is around causality, where primarily I'm leading that effort. One is around safety, and one is around explainability. So with that, I'll be very happy to take the questions.
Thank you, Dr. Sirin Banerjee, for your wonderful talk. I hope that students and faculties, they will know some things from your talk. So we have some questions, and we have also Dr. Indranil Hatai, who will be conducting these sessions. So a few questions are there from the participants. Okay. So the first question that is asked by Stania Sharma. So she wants to know, please suggest how can we use fault tolerance in communication system? Just a minute,
Yes. So this comes primarily under verification. So there is another researcher. He's a principal researcher. So he's working primarily on this system. So I can just give you a glimpse of what we do in fault tolerance. So basically, when we have and I'm only telling from AI machine learning perspective. I mean, there are fault tolerance algorithms and, in control systems also, which is today traditionally used in the networks today. But from AI/ML, what we are trying to do, whenever you have a model, maybe it's a supervised learning model, maybe it's a reinforcement learning model, especially for reinforcement learning model, there are infinite possible states, and not all those states will give you good results. So that's why, he can actually set boundaries that, okay, I will not let my RL model to use that. So it has to be all the training, data points, or maybe during the training process, the actions and the state has to be a bound. So he can set a bound and make sure that all these AI agents remain in the bound. So fault tolerance is like, okay, as soon as I see some of those data points crossing that boundary, then we can, say that, okay, don't go there. So it's like, that's how we maintain safety and fault tolerance. Another aspect which I am also working in with him is, can we find out causal reasoning for these fault mitigations? So basically, okay, verification is one approach, but can we find out underneath causal relationships? And that remains true across the vendors, because today I take Vodafone data and build an algorithm. When I get Airtel data, it will be, there'll be a significant change in distribution of the data. So even if we have built a fault tolerance or a validation system on the Vodafone data, when I change the vendor, it will not, those conditions may not hold true. So can I even go back one step further and find out what was the causal relationship which made us lead to that boundary? And that causal relationship, the hope is that that will remain invariant. So these are the ways, we can build in fault tolerance systems for AI and ML. Does that answer your question?
Miss Tania?
Yes, ma'am. Yes, ma'am.
Any more questions from your side?
No, ma'am. Thank you.
Okay. Now, Dr. Satish Tiwari is the faculty at ECE department at SRM University. Some questions for you. Dr. Satish, are you there?
Yeah, I'm audible.
Yeah, you are audible. You can ask the
Okay. Good morning, ma'am. It's Dr. Satish Tiwari. First of all, ma'am, thank you very much for this informative session. I can relate because in my master's, I was having this thesis work based on this carrier aggregation. But at that point of time, I was not having clear idea how I'm going to do research in that. But after seeing your talk, I have a question, ma'am. I assume that whatever this interference modeling we use in this mobile communication, And here you are using this artificial intelligence to reduce the interference. But I want to know how this type of technique can be used in a scenario where we have signal dependent interference as well as noise. And that
Yeah.
too when it is time varying.
Yes.
Like in case we have molecular communication these days, we talk about that it is going to provide a different physical layer in the upcoming 6G technologies, where we need biocompatibility, some in-body communication. So there even a part of signal is interference. It is signal dependent and that to time varying. So ma'am, can you just give some information how we can use techniques similar to the whichever you have presented, so
Yes.
that interference is mitigated in that scenario also?
Yes, yes. So technically we call this as correlated noise, that when you have the noise, like it's correlated with the signal. And I agree with you, it's very difficult. And even in like my background before doing work in communication was image processing, there we also have the same thing. Like wherever we have an image edge, the noise around it is higher. It's very difficult because then your noise, actually, if you want to do anything with the noise, your signal also gets affected. So for correlated noise, basically the promise that we see in AI/ML is that AI/ML is a more data-driven approach and it can model non-linearities. So traditionally, we will say that the noise is additive wide Gaussian, right? Then it becomes a very simplistic model. First of all, it's additive, and real life, it doesn't work for correlated noise. It's not additive, it's multiplicative, and it's correlated to the signal. So we are trying AI/ML models. There are ways, like in image processing, we have AI/ML algorithms for zipper artifact removal, where also it's like it's a correlated noise. Similarly, here also for time series, we are trying to model from the data that if it can learn out what is the signal and what is the noise. So Fourier frequency mapping, that also is one way, because since we are dividing it into the frequency range and the noise, we know both the noise and the high frequency signal is important. So yeah, AI/ML is one thing we are trying. Another thing we are trying more recently, we are still work in progress, is around causality. So causality has huge hope in the sense like, okay, if we found out the causal relationship, for example, in the channel estimation scenario, what happens is like when we change the power, the channel appears better. So instead of just modeling the signal and the noise with observational data, can I, with a causal relationship, map the variation in power to the variation in signal? So the hope is that when we model the causal relationship between power and channel, instead of just the observational data, it will take care of the noise. Because though, like when we increase the power, like there'll be a change in the signal, the noise will be uncorrelated. So in the observational data, the noise will be correlated, but when we are trying to draw the causal graph will remain uncorrelated with the noise. So that's again something which is work in progress. So I'll be very happy to, if we have a publicly available paper, probably we'll talk about that. But that's one way, like we model the causal relationship and hopefully that causal structure will be able to separate the correlated noise. So that is more on the correlated noise part. The time varying part is actually we encounter it in almost every situation, because we call it change of distribution, or the word for it is, I'm forgetting the exact term, but domain adaptation. So basically, and it happens, for radio, it happens like, if you take 1 day's worth of data, you will see 3 distributions and it changed during the day. You're talking to phone, a truck comes by, your distribution has changed in your data. So there we have, Kale divergence method. So these are more classical approaches like Kale divergence method to find out how your distribution is changing and then adapt your algorithm based on that. These are classical approaches. We are trying to have AI models also to calculate these change of distribution. And more recently, we are trying to do a causal approach. Causal approach is like, instead of doing a direct auto encoding, we are doing a causal auto encoding. And again, the hope is there, the causal structure will remain unchanged, even if the observational data changes distribution. So that's how, but this is a problem which it's very relevant, like how when distribution changes, how do we address it?
Okay, thank you, ma'am. Ma'am, just for curiosity, I would like to know, since I'm doing research in molecular communication, and there are magazines and articles where they claim that 6G is in 6G we'll have this molecular communication, where it is going to provide a different physical layer where we need biocompatibility, like some in-body communication using molecules, chemical. So, ma'am, is there a practical work even into consideration within this erection,
Yes,
or not?
yes,
I mean,
yes.
or it's totally something
No,
which will take time?
No, it is going on. It's going on mainly in research. So there's a little bit of difference between research and products we have. And that's why, my past experience in Ericsson, like I was in Gaia. So Gaia's charter was we were supposed to work directly on the business problems. But in research, we are allowed to work on little bit futuristic, may or may not go in research. So though in the business unit, it's not happening, biocommunications is very active topic in the research. And we have demoed the, things like that. It looks very cool, like, robots are being managed and, person is talking and they are seeing an avatar of the same person on the other side in real time. So we have very, very nice demos inside Ericsson research, but it is an active area of research.
Okay, thank you, ma'am. And one more thing, ma'am, I would like to know, since I am this internship coordinator for this ECE department at SRM University. So I would like to know, ma'am, is there an opportunity for our BTech students for the internship at Ericsson?
Yeah, so I am not the primary person who kind of makes these decisions. So my manager actually makes these decisions, but we do get students. So this time we are getting 2 students from IIT Tirupati and 1 student from Amrita University. So what
Okay.
I will do is I will go and talk to my manager and then put you in touch with him. So the
Okay.
process is very similar. Like we get a list from the university who all are the students who are interested. Then we have a 30 minutes discussion with the students. And then if there's mutual, if they like our work, we like them, then we just select. So it is
Okay.
very much possible, but I will, have to talk to my manager.
Okay, ma'am. Thank you, ma'am. I will like to write mail in this regard so
Sure.
that things, if it is possible, it works.
Sure.
Okay, thank you, ma'am.
This is Dr. Uday. This is Dr. Uday here, Assistant Professor in ECE department. So I did PhD from IISc Bangalore in the area of resource allocation, wireless communications, and GMTV. Currently, I am working on the project related to IoT, ITU, where we are doing on the very interesting group for this industrial 4.0 case. This for their emergency users will be there, their non-emergency users will be there. We need to allocate. So we are doing that. So that is first we are looking for this some large number of users are there. First we are doing time scheduling using auction TV. Then afterwards we are doing resource allocation using GMTV. Resource allocation means power control or sub-channel allocation. So once we do this, next phase is this making the machine to learn this. So this optimization points and doing that. So this is the work which we are doing. We'd like to collaborate in this direction. Is it okay to discuss with you privately or something? Yeah. Because I and my friend Vishnu, he is from ITU side. So I'm from SRM side. We are working on that project.
Yeah, definitely. I mean, whenever we go to, present any conference or any present in a talk, like we also want to collaborate with universities. It's a win-win situation, but only I'm not the decision maker. So I will take these inputs to my manager. If you want to write a mail, it'll be very good. I can, forward the mail to my manager, but he will be the main person who will be.
Sure. What I'll do is I'll send a mail abstract of that work so that we can have a discussion.
Yes.
We are looking for the collaboration only. We are looking for collaboration only for the work because it's a very big work.
Yes.
So we are divided. Some students are working in the project for the simulation side. Algorithm side, me and one more professor from IIT in Lucknow, and this person we are working now currently.
Yes.
So that's the reason we're looking for some of the collaborators. So that we have a lot of things and create a prototype.
Yes, yes, definitely, definitely. I'll
Sure.
follow up. I will follow up. But all these topics, are very close to our this. We also have a lot of projects in IoT, and there are many challenges which actually we feel like in industry we cannot, go into deep mathematical modeling. We always have to show something that works. But if we have academia partners who can go more deeper into the mathematics of it, it's easier for us. So I'll talk
We're
to
looking
my
into mathematics, so deeper mathematics.
yes, yes, yes. So definitely, I will.
Auction theory part we are looking currently. So time scheduling of users. It's complete new model we are looking at it. So that's the reason. So we like to
Sure, definitely, I will follow.
Thank you.
Ma'am, we have Dr. Shivendu Samantu also. He has some questions. Dr.
The
Shivendu Samantu, are you there?
I'm there. Okay.
Please ask the question.
Nice talk, Banerjee. That is the one thing about that. And I have little bit discuss about this noise interference. That is the interference diagnostic system. Can you repeat again this one? I am missing something actually. That is the interference diagnostic systems that you have discussed in the slide 3 or 4 or 5, I think.
Let me go back.
Yeah.
Slide. Which slide you want? Slide.
That is the block diagram is there. So that lower. This one. 10. Yeah.
Okay. So basically here we have separated the static and the dynamic interference. The static interference is like pattern like this, the red line.
Okay.
Very clearly different from the dynamic interference, which is shown in green, right? So this block diagram, like this block separates that. Post that, the dynamic part, we send it like this is 3 time series coming out. The first is interference from the primary cell, second is from the first neighbor, third is from the second neighbor. And if we have n neighbors, we have n time series. So then distance based method will do dynamic time warping. Frequency based method will do a wavelet decomposition or short time Fourier time transform decomposition. And sequence modeling will do HMM or LSTM based modeling.
Means we have to apply all 3 one by one or one of them?
Parallelly. First we apply parallelly. Here I'm showing you the results. So we apply parallelly because if noise is high, then frequency will not do well because noise was also very high. So it's very difficult to separate which is signal, which is not. But here dynamic time. So first we apply all of them parallelly. Then the confidence measure block will kind of, from the results, it will try to find like, okay, what is the best combination?
Okay. That's I am thinking that the combine of all these things. Okay, we have the parallel, we have to done this one, then we have to judge which one is best. That is so. Yeah.
Yes.
Okay, thank you. That is the thing I needed actually. That is I'm missing for this one. Okay, thank you, ma'am.
Sure.
Ma'am, we have Dr. Anirban Ghosh also. He wants to ask you some question. Dr. Anirban, you are there?
Yes, I'm there.
Please ask your question.
Good afternoon, Dr. Banerjee. It's a very fascinating talk. It's really nice to see how the industry is working on the theoretical aspects of the problems we work on. So I think I almost got my question answered in the answer that you gave to Dr. Satish. I just want to make sure if I got it right. So you mentioned that there are 2 approaches that is there. One is based on the observational data that the decision is made. Another one is based on the cause of why the fault tolerance or thing is happening. So my interest is like there are a lot of things that can cause a particular fault or a particular interference and things like that. So how do you people actually manage to account for all the different causes?
Yeah, very good question. Actually, we are doing using again 2-part approach. One is we are doing causal multi-RL agent problem. So though here I told you, okay, this part is static, this part is dynamic, and I can take the static part separately. That's not the case in reality. Yeah, 50% of the time this is the reality. usually what happens, okay, one cell went down, so okay, that part became static, other cell was affected by that, and there are multiple causes. So and there are something called confounders. Confounders is like, for example, a pilot is driving a plane on a windy day, right? It will constantly tilt its handle. But when we try to model it, the handle tilt is not real. The handle tilt happened because wind was flowing. So we have to take care of that. So there's multiple hidden confounders and multiple hidden causes. We are trying to have both RL and ML models take care of it. So it's called multi-agent RL models with causal analysis and multiple hidden confounders and multiple causes for time series analysis. So all this is work in progress. So we will see. But very good question. It's very relevant question. Like, it's more difficult than what I showed you.
Okay. Thank you so much.
Yeah, ma'am, we have also Dr. Sunil also there. Sunil, I have a question for you. Sunil, are you there?
Yes, I'm there. Good afternoon, Dr. Serene. Yeah, so it was a very nice talk. So I am Dr. Sunil here. I am from the ECE department. So I think in your talk you mentioned about this network service providers hiding their operating frequency from other network operators. So may I know what is the reason behind that? Like, it's quite open. I mean, in my opinion, they're not hiding. That's so. I just wanted to know. Yeah.
They will hide. One is business. It's very expensive. I don't want, ultimately Airtel also wants to make money. Vodafone also wants to make money.
Of course, they are getting that spectrum in the auction, right?
Even after they get, so I'll tell you. So one is business. Okay, one is pure money. The other part is like, even if I am Airtel, like, that's why the frequency hopping was invented, and that too way back in Second World War time. There are many intruders, and especially for military communication. Initially, it was only done for frequency hopping, was only done for military communication, but only nowadays networks also have the same frequency hopping. So because right now we have so many cells, and we often see data like where somebody tapped, and it's very easy to tap the network. I mean, it's all in the electronic form. Like, you tap one network, you can, like, there could be denial of service attacks, there could be signaling storm attacks. Like, it's very easy for anybody to fake and create that, okay, there were multiple cells when all those cells were not existing. So that's why, like, mainly it comes from two reasons. More than money, it's for security. So that's why, like, nobody will want to share when they are communicating on a certain frequency and they keep changing, like this, using frequency hopping, is to keep, attackers at bay.
Okay, but is it sometimes like when you move from one network to another network, sometimes this network even help each other, like for a customer?
Yeah. So that's handover management. Yeah, yes. That is definitely, that handover management has to happen. And actually, like, the phone remains connected to two base stations during that handover, because we have something called ping pong effect. If it was like immediate, again, you can, if you keep walking up and down, it will start switching. So all those handshakes happen. But having said that, I mean, they have to worry a lot about security. Even during this recent Ukraine war, like, there was somebody who hacked the security systems, and it's a big loss when these hacks happen. It's a big loss. So there is a separate AI ML group, inside Ericsson, who just work on security aspects, and they are making it harder and harder for intruders to break through.
Okay.
So that's the main reason they like, it's not good if they keep sharing everything.
Okay, thank you, Dr. Saren. Yeah. So that's it from my end, Dr. Manoj.
Okay.
Yeah.
Thank you, Dr. Sunil. Yeah, Dr. Anuj has a question for you. Dr. Anuj, you want to ask some question?
Yeah. So Good morning, Dr. Banerjee. Actually, my question is was actually asked by Dr. Satish about internship. So I guess if you get
Yes.
email from him, please tell us so that we can communicate with our students. One more thing, what do you suggest our students to prepare? Let's say if they want to work for a company, or let's say if they want to do internship, what topics they should be working on as a bachelor student?
Yeah, so that's a very interesting question. And, first thing is like, I would say, I don't know. I mean, I shouldn't say this, but somehow I find we as Indian students are very much spoon fed. Okay. First tip I will give, like, first think through what you want to do. Do something just because you want to do it. Because if you have the interest, learning part, Indians are very intelligent. They will learn it up. But if they don't have the interest, we can push as professors, we can push from industry. It won't happen. It'll be always like this, chase. So I would say, think through it. If you really like it, yes, definitely go for it. Right now, machine learning, knowing the deep depth of machine learning, not only using and building these models, have a deep, since you are coming from a, academic institute, try to understand the maths behind it. Because this problem, this PIM given environmental unknowns, we first showed a binary search method, but right now what we are doing is we are doing a mathematical breakup of this problem and trying to find a mathematical model which actually solves this. And the good part of that, if we get the maths right, it will not only solve this problem, it will solve other problems as well. So that's why I would say one thing is focus very strongly on the maths. Signal processing is always a plus. So I also came from image processing background, and when I shifted to communication, the shift was easy because I understood the image processing, and it's not difficult. Like, it's one is 2D, one is 1D. So that's, I would be my suggestion, like get your basics very, very solid. If you have the interest, know the maths well, know the signal processing well. Tools you can always learn. But the fundamentals are like very important. You be very, very clear. Physics, so much physics we have, even the passive intermodulation explanation. There's another problem which I'm working on is congestion control. It's just a maths and physics, like class 12 maths and physics. If somebody understands maths and physics well, they have a huge edge over anybody else. So that would be my suggestion, get your basics right, and maths, physics, science, signal processing. Yeah, try to learn as much as you want to learn.
Yeah, that's great to hear, Dr. Banerjee, because we as a faculty also enforce to learn mathematics, but students mostly, they want to implement something, they download something from internet, just work with it, and that's all.
Yeah.
So that, I think if students are listening this, they should take this very seriously now and start studying maths.
Yeah, no, I will share another perspective. It happened 2 days back, and it's not to make anyone feel ashamed about it. Just like for internship only, I got a bunch of 12 resumes. I saw they were RMO winners, regional maths Olympiad winners, coming from Chennai Narayan Techno University School. Okay, which is like right next to our house. I know how good school it is. IMO winner. And then once they get into college, third year CGPA is 6 out of 10. I was feeling like, as your parent, when your parent put you in a good school, you did so well. And once you're in college, you're coming with a CGPA of 6. Why should I even, consider you for an internship? So it's very, I know it's a problem, but that I would say, like, keep that motivation alive. Like, it shouldn't be like, because my mother and father told me to study engineering, I'm studying engineering. Do it because you love it, and keep that spirit. When a person won a international maths Olympiad or physics Olympiad, I cannot believe that person is even eligible for a 6 out of 10 CGPA. So
that's true.
Yeah, so I'm really sorry, but I didn't want to hurt anyone, but that's
the fact.
Yeah.
Okay, thank you.
Madam, we have 2 more questions, one from Dr. Anirban and Dr. Shivendu.
So that is the almost same question. That is Dr. I am Dr. Shivendu. So Dr. Banerjee, that is any publication related to this block diagram that is you have used for 10 number of slide
Yes.
number. Any
Yes, yes,
facilitation
yes.
needed there?
I will send the list. These are all, I will send the list. These are all in IEEE. If you go and search my name, or I will send the list.
No, that is the specially 10 number, slide number 10 that related
Yes,
to
yes.
this one.
That's
Actually, this
already published paper.
published
So
now. Okay, then I will find out. That is the one thing.
So we presented this work in a conference which happened in Bangalore in January called ComNets.
Yeah.
So like you can see in the proceedings in IEEE Explore is there. I'll send a link also to all my publications.
Okay, thank you. That is I needed actually. Okay, thank you. That is my questions.
Sure.
Nariman sir, you can ask. Yeah.
I think you already did. We are just keeping our waiting by all these questions. That thing, and if it is possible to share your email ID, that would be also great.
Yes. My email ID is my first name, Serene, and my last name. So here, serene.banerjee@ericsson.com. So my first name dot my last name @ericsson.com.
I will share the mail ID to all of you. No problem.
Yes.
Ma'am, we have Tanya Sharma. She wants to ask you some question.
Yes.
Tanya, are you there?
Yes, sir.
Please ask the question.
Ma'am, I'm doing MTech in VLSI industry. So do I have any opportunity regarding internship?
Of course. MTech students are better because usually if your professor also agrees, we can have, because BTech students, we can only keep them for 2.5 months. MTech students, if professor agrees, they can work for a longer time, 6 months. So just send me a mail. I will follow it up with my manager.
Sure, ma'am. Thank you.
Yes.
Any more questions from the attendees? Okay. Ma'am, I want to ask you some questions. Now this machine learning AI, they're using mostly this statistics, right?
Yes.
But now it comes in the computer science domain. So how to differentiate whether computer science or statistics?
Yeah, so this is a very good question, because even this band depth validation, I talked about here in this slide, the band depth validation. So we have one person in our, actually not one, 2 people in our team who are PhDs from ISI Kolkata. So, and they are statisticians. So we work like any model we build, we talk to them, and they will have, statistical models to solve the same problems. So it is similar. Subtle differences, non-linearity modeling, I would say it's better if it's data-driven. Statistical modeling usually makes assumptions which don't hold good in real life, especially when we have out of distribution samples and things like that. But yeah, statistics influences us a lot. So we try to, in our work, we try to like they specifically, since they are PhDs from ISI Kolkata, they understand the statistics part of it. So we work jointly with them.
Okay, ma'am. Now I'll be asking some questions not relevant to this research topic or other things. So as you see that nowadays, very few number of women are there in the higher studies and research, especially in the research domain. So what is your opinion on this one? And how will you encourage the students, women students or girl students, to do for higher studies and research, especially join the industries? So please elaborate these things so the students can.
So for me, like personally, this question is not relevant at all. And, that's, I would say, a blessing from my family. In my family, I have 7 aunties and 1 uncle, and all the 7 aunties are PhDs, including my mother. So, for me, having, seeing women do science is not a big deal at all. But this is a very big topic. I mean, many people talk about it. What I see is, one thing is there's a fear factor. I don't know why. Like usually, women, again, I cannot relate to that, because in my house, I saw, there was no distinction between men and women. So for me, this distinction never arose in the first place. But usually when I talk to students or when I talk to other colleagues who are the first ladies who came out, they say that, there are inherent biases, like, okay, you cannot do maths, men will be good at maths. Maths is something which is very scary. But it's not like that. It's not like that. I mean, brain, inside, if we go in the brain, who's woman, who's man? I mean, as long as you can think, you can do. So, but good thing in Ericsson is like here, we have, in our group also, we have 2 PhDs, ladies. So second person is Anusha. She's very, very strong in maths. So yeah, I mean, I would just say that just push yourself. Don't even think that you're a woman. That's the best I can say. Because at the end of the day, I mean, your publication, your work will talk. I mean, who cares whether it's women, man, child, old, adult? All these are external labels, right? So if you do something fruitful and world is happy with it, that's it.
Any more questions from any more questions? Okay, I'll ask Dr. Kunjal Hatai to conclude the session.
Thank you, actually. Actually, thank you, Dr. Banerjee, for your immense knowledge, which you shared with all our faculties and the students. And actually, I just want to say, don't forget us. So I hope that all the students and the teachers, they will be more interested to work with you and or the Ericsson. So you can get or you can expect a lot of emails from our side. So I hope that in future we can have some collaboration or we can have actually the guidance from you. So, and thank you from my side for accepting my invitation. And it was a nice talk and wonderful talk.
Thank you so much for inviting me. It's my pleasure also, and I'll definitely keep in touch.
Okay, ma'am.
Thank you, ma'am, again for giving the first, you delivered the first lectures on industry in academia lectures. We hope to see you in the coming in the classes also that will be organized by our institute, our department. So you can teach our students also, as well as we are also going to organize one conference in the December month. So we hope that you will be present there. And especially we want to organize some industry session as well as one women's session also. So please lead us in that session.
Sure. Thank you so much. Thank you so much once again.
Thank you everyone for joining the sessions. We can end the session. Thank you, ma'am.
Thank you very much. Thank you.